In November 1895, Wilhelm Röntgen discovered X-rays while working at the University of Würzburg in Germany. He was working with cathode tubes when he noticed that while it was on, a fluorescent barium platinoside screen would begin to glow. However, the tubes were too far away from the screen to affect it. He was amazed by it and began to investigate this phenomenon in secret. By the end of the year, he dubbed these X-rays and described three characteristics in particular. According to the University of Cambridge, these were: 1. They are very penetrating and were able to pass through materials that are opaque to visible light. 2. Invisible to the human eye. 3. Would cause many types of material to fluorescence and could be recorded on photographic paper. His discovery shook the science world, and X-rays were soon reproduced in laboratories all around the world. The first question was whether the X-rays behaved as waves or particles. One physicist who studied the rays was Max von Ley in Germany. Ley believed that X-rays were waves similar to light and not some form of particle. Von Ley's colleague, Wilhelm Wien, calculated that the wavelength should be around 100 of a nanometer, 10,000 times shorter than the wavelength of visible light. Since for diffraction to occur, the slit size had to be smaller than the wavelength of the wave, normal slit experiments would not work. According to root netting, X-rays have very small wavelengths between 0.03 and 3 nanometers, so small that some X-rays are no bigger than a single atom of many elements. According to Young and Friedman, about the same time, the idea began to emerge that in a crystalline solid, the atoms are arranged in a regular repeating pattern, with spacing between adjacent atoms also of the order of 10 to the power of minus 10. Soon von Ley realized that a crystal could be used as a diffraction grating for X-rays. To test this, X-rays were allowed into a lead box containing a crystal, with sensitive film behind and to the sides. When the films were developed, there was a large central point from the incident X-ray, but also many smaller points in a regular pattern. These could only be due to the diffraction of the incident beam and the interference of many beams. However, there were a large number of points where these spots appeared to be missing. To explain this, von Ley suggested that the X-rays must contain only certain wavelengths to account for the missing diffracted beams. However, a young Cambridge student didn't agree with this and began investigating von Ley's X-rays patterns. This student was William Lawrence Bragg. Lawrence Bragg taught that X-rays must be made up of a continuous spectrum of all possible wavelengths, in the same way that white light is made up of a spectrum of all the possible colors. Therefore, if there were any missing patterns, it would be because of some property of the crystal. Before going further, let us explain what the structure of a crystal is like. According to Stowe and Jarrett, when atoms are arranged in a regular pattern, a geometrical solid, known as a unit cell, is repeated in 3 dimensions and therefore forming a crystal. These crystals consist of planes of atoms that are spaced a distance d apart. So, according to Halliday and Resnick, when an X-ray enters the crystal, the rays of the incident beam are always parallel and in phase, up to the point at which the top beam strikes the top layer at atom D. The second beam continues to the next layer where it is scattered by atom B. The second beam must travel the extra distance AB plus BC if the two beams are to continue traveling adjacent and parallel. This extra distance must be a whole number multiple m of the wavelength for the two phases of the two beams to be the same. Therefore, m lambda equals AB plus BC. Since AB equals BC, m lambda equals 2AB. Also, sine theta is equal to AB on D, and D sine theta is equal to AB. Therefore, m lambda equals 2D sine theta. This is what is known as Bragg's law. So when X-rays are diffracted on a screen, the bright spots are because of constructive interference. The dark spots are when destructive interference occurs. This technique is used to determine the structure of crystals in a process known as X-ray crystallography or X-ray diffraction.